This is both an awesome and complicated problem, but overall, I would say awesome. This is OpenStack Physics College Physics Chapter 7, problem number 69. And of course, I wrote down some of this stuff because otherwise it gets a little boring. So here's the general situation. You have a person that crouches down and then jumps, just like I did right there. And we want to find the velocity when they leave the ground. We want to find the force the floor exerts on them, and we want to find the power. Those are great questions. Okay, so let's start off. And why are we doing this as a work energy problem? Well, except for power, there's no time involved. And if we don't have time involved, we want to use the work energy principle. There are some issues that we need to work out that aren't fully addressed, and people kind of just gloss over them. I'm not going to gloss over them. I'm going to tell you all the issues. Okay. So let's break this down with a picture. The picture is the best way to start. I have here the basketball jumper in the crouched phase. So they're down like this. You can't even see me. And we're going to treat the person as a point particle, which obviously is not true. But in this case, we're going to do that. Okay, so they're just a point. And we have to do that because imagine that they're not a point. How could I calculate the work done by the floor if the floor doesn't move? I can't. Okay. But anyway, so here's my point, and it's not clear. They said they crouch down 0.4 meters, and then they jump up after that 0.95 meters. So I picked this is 0.4 meters below this center of mass at position 2, where they're just leaving the ground. So position 1, crouched, and then they jump in slow motion, and then they're leaving the ground. So this is the point right when they're leaving the ground. And then after that, they rise up here, and then they are no longer leaving the ground. And that, I'm going to say, is 0.95 meters above that position. Now, that could be wrong, and it feels a little high. I mean, that's pretty high. If your center of mass goes 1 meter up, yeah, I'm not going to do that. Okay, but anyway, whatever. It's a basketball player. Okay, we also know the mass. I didn't put the mass here. The mass is 105 kilograms. So, I mean, that's pretty large mass. Okay. Now, we want to find the velocity at position 2. So, how do we do that? Well, we can work backwards, right? If we just want to find the velocity when they leave the ground, it doesn't really matter about the jumping. I can just go from point 2 to point 3, and I can use the work energy principle. So the work energy principle said the work is the change in energy. We need to pick our system. In this case, I'm going to pick the player plus the Earth. And by including the Earth in my system, then I don't have to worry about the work done by the gravitational force, and I can instead include a gravitational potential energy, and that just makes things a lot easier. However, when they're jumping during this part going from here to here, there will be work done on the person. We're cheating by making them a particle, and that will be the work done by the floor. But for this point, we don't even care. Okay, we're just going from 2 to 3. So from 2 to 3, what forces are acting on the person? It's just the gravitational force. And we do not do work done by gravitational force because it's part of the system. So that means that we can write 0 work is the change in kinetic energy plus change in gravitational potential energy. And remember, kinetic energy is 1/2 mv squared. Gravitational potential energy, I'm just going to call it U because there's no other potentials, is mgy. That's a change in gravitational potential that we care about, and that's just a y. So we have to pick where y is equal to 0. It doesn't matter where y is equal to 0, but you have to pick and stick with it. So I'm just going to pick y is 0 right here. I don't know. I just picked it. Okay. Yeah, and I'm gonna write it out the full way. Okay. So right here, what about the kinetic energy? They're moving with some velocity v2, and I'm going to write it as a scalar value because it doesn't really matter because we're dealing with work energy, which is a scalar equation. It doesn't depend on direction. And then up here, v3 at the highest point is 0. So the kinetic energy right there is going to be 0. So let's write this out. 0, the work done, k2 minus k1 plus u2 minus u1. Now I'm going to start putting in my values. Okay, I already said k2. Oh, this is technically, let's be legit here. I'm going from 2 to 3 just to keep things nice. 0 is K3 minus K2 plus U3 minus U2. That way they'll match up with these numbers right there. Okay. I already said K3 was 0, but those are not. So I have 0 equals 0 minus 1/2 m v2 squared, that's the kinetic energy at point 2, plus mg y3 minus mg y2. And so over here, let's just put y1 is 0, y2 is 0.4, y3 is 0.4 plus 0.95 meters. Okay, so I'm going to put in the numbers just like they are because that's fine. So let's add this to both sides. I get 1/2 m v2 squared equals mg, and I'm actually going to factor this out because it makes sense, y3 minus y2. Right, I can factor out the mg. The mass cancels. I can multiply both sides by 2 and take the square root, and I get v2 is the square root of 2g y3 minus y2. And, you know, if you're thinking, hey, that looks a lot like the kinematic equation that I didn't like at the beginning, and it is the kinematic equation that I didn't like at the beginning, if you have an acceleration of negative 9.8, which you do because they're slowing down. Okay. That's where that, I mean, it's not where it comes from, but it's the same thing. But I want to do it as a work energy problem. Okay, let's put in our values here. So I have the square root of 2, 9.8. Am I running out of room? No, I'm good. And then I have the height y3 is 0.95 plus 0.4. I'm going to write it out 0.95 plus 0.4. Running out of room now. And then minus 0.4. And so those cancel, which is kind of nice, not entirely needed. So if I put this in my calculator, drop, 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 drop. Okay, so that's going to be equal to 2, enter 9.8 times 0.95. I'm not going to do the 0.4 because I already told you that cancels. Times, and then square root. 4.3, I'll just go with 4.3 meters per second. We're going to need that later, actually. Okay, and we're going to need it now. Okay. So that was the first part. And again, you didn't have to use work energy. I like work energy. You could have just said, I'm going to calculate the acceleration, it's free fall, it's projectile motion, I'm going to use kinematic equations. That's fine. That's what's nice about physics. There's multiple ways to do things. Unless it was a test and it said, use the work energy principle, and you did that, it can't be wrong. It's not wrong. Unless the person grading the test is just mean, but hopefully not. Okay, let's go on to part B. I'm going to write those. We know what those are. Okay. So for part B, what's the force exerted on this person? I'm going to draw a force diagram for the person while they are jumping. So here's while they're jumping. There's a downward gravitational force, mg, and then there's an upwards force from the floor pushing up. And so this is assuming the person is a point particle, which they're not, but it's going to work out fine. And we know that the person's accelerating, right? They have to be accelerating because they're going from 0 speed to jumping speed. And we know what that speed is. We know v2. So again, you could actually calculate the acceleration here, but I'm not going to. Instead, we're going to use the work energy principle like before. And the same system, but now we are going to have work done on the system. And the work done is going to be the force from the floor times the displacement. So remember, work is F delta R cosine theta. So that's the force, that's the displacement, and that's the angle between the force and the direction they're moving. So in this case, the force is pushing up, the object's moving up, those are in the same direction, so theta is 0. Cosine of 0 is 1. So that's good. So let's call this work done by the floor. And then I have the types of energy. I'm going to again have a change in kinetic energy, and a change in potential energy. So let's put this all together. I have the force from the floor. I'm just going to call it F just to make it look nicer. And then the change in position is going to be y2 minus y1, right? They're going from here to there. So this is going to be 0.4 meters. Now, if you have to be careful here, this is technically the magnitude of the displacement. So if you got a negative number here, we already said it's going to be a positive work, so just make it positive. This is going to be positive the way we did it. But there's some stuff that the book doesn't tell you. Okay, this is not the best definition of work. I'll go ahead and tell you fine. The work is actually defined as F dot delta R. This is the dot product. I'll make a video about that just in case, because it's a nice way to look at it for future things. But I'm trying to match up with OpenStax college physics, which it's not I don't agree 100% with, but it is online and it is free. So that's a thumbs up for that. There we go. Okay. So that's the work done by the floor. And now that's going to be equal to the change in kinetic energy. I'm just going to write it out as K2 minus K1 plus the change in gravitational potential energy, U2 minus U1. Right? We can't forget that. It's not just the floor making the person accelerate. It's the floor and gravity's pulling on them too. Now, some of these things are zero. The way we did our y values, the y1 is 0. So u1 is 0. Also, the person's going to start at rest. So the kinetic energy at that point is 0. They're not at rest up here. So now I have F y2 minus y1 equals K2 1/2 m v2 squared, which I know, and then plus mg y2, which I know is 0.4. And I want to solve for F. So F is going to be equal to, let's just write this out. It looks a little messy. 1/2 m v2 squared plus mg y2 divided by, and y1 is 0, so I'm just going to put this as y2. And so yeah, you could cancel that, but you can't cancel right there. So let's just put in our values. 1/2, 105 kilograms. I'm going to use this velocity, which you could have put it in as an expression, but I'm just doing it the way most people think. They like to think with numbers. So 4.3 meters per second squared, that's a 4. Squared, that's that. And then I have plus 105, 9.8, 0.4. Ooh, that was close. And all of this divided by 0.4. So let's just put it in the calculator that way and calculate this for us. Okay. Drop. So I have 0.5 enter 105 times 4.3 squared times 105 enter 9.8 times 0.4 times plus 0.4 divided by. I have, it's huge. 3455. 3455 newtons. That seems like a lot, but the weight is 105 times 9.8, so 105 enter 9.8 times. The weight, the gravitational force is 1,000. So this is just 3 times the gravitational force. You're going to have to do that in order to jump, and that's fine. So let's put that right here. That's the force the floor exerts on the person, but that's also the force the person exerts on the floor when they're jumping. That's important. Okay, what about part C, the power during the jump? Well, we define power as the change in energy with respect to time. So if I go from position 1 to 2, I can calculate the change in energy. And does the question say the power of the person or what was the player's power output? Okay, so in this case, I'm actually going to write this as work over delta T, and that's going to be the work done by the floor, which is the work done by the person, because the floor doesn't really make the person jump. It's not the floor doing the work, it's the person. And we just calculated it as the floor because we assumed the person was a particle. That's fine. So that is going to be different than the change in energy because we're not going to include the work done by gravity. Wait, yeah, we're going to use that. We're not going to just look at the change in kinetic energy. Okay, so we have that force over that distance is the work. The work is going to be F times delta Y. So we can calculate that. But what about the time? The time is tough, right? Because here they're starting and they're going. We know the distance. So let's say V average in the Y direction is delta Y over delta T. And let's also say this is equal to V2 plus V1 over 2. It's the average. Now that's not true. The person probably is not moving at a constant rate of change. You can't actually do this, but you can. It will give you the average though. Okay. We know V1 is 0. I know V2. I know delta Y. So let's solve this for delta T. Delta T is going to be equal to 2 delta Y. I'm doing this in my head. Move that up there. Divided by V2. And again, this is problematic as a vector because you'd be dividing by a vector, which you don't want to do, but you have to do it as a component. Let's put it all together. So the power is the work F delta Y divided by the time 2 delta Y V2. The delta Y's cancel. I think that's okay because we know the velocity. And force times velocity gives us units of power. It does, right? Because that's newtons times meters is a joule divided by seconds is watts. So that's good. So I get 1/2 times the force 34.55 times the velocity of 4.3. I'm going to tell you something after this. Don't even forget. 0.5 enter. 3455 times 4.3 times. Oops, I did divide it by. Okay, 0.5 enter. I can't see the calculator very well. 0.5 enter. 3455 times 4.3 times. And I get 7428. 7428 watts. I do want to do one thing really quickly. We know this jump height. Actually, I'm going to give this as a homework to the homework because I'm not going to solve it. Well, let's talk about this. That's huge. 7,000 watts is huge. Okay. But it's over a very, very small time interval. Let's just calculate that time. 2 times 0.4 divided by 4.3. What's the time that this person takes to jump? 2, I could have done that in my head, times 4.3 divided by 0.18 seconds. So over that short of a time interval, humans are able to exert huge powers. But over an extended amount of time, we're talking more of a power of about 100 to 200 watts, maybe 300 watts if you're super awesome. Okay, so that's that problem. Now, I'm going to give you a bonus question, which is really the same thing, right? This analysis doesn't matter if it's a jumping player. And instead, what if I want to do something like this? That's the Hulk. And the Hulk jumps. I guess I should draw like that. We can do the same thing. The Hulk's hulkier, right? The Hulk from the Avengers. Or the Hulk movie, there. And the Hulk can jump really, really high. Okay, so you could estimate how high the Hulk jumps. You can estimate this distance, because, the Hulk's big, but you can still estimate his size. And then, it's the same problem, right? You still have 1, 2, 3, just like that. And you can estimate how high he jumps, this, everything. And what I would do is to calculate the force in the same way. And what you find, because I did it, what you find is the force is huge. It's the Hulk, right? The Hulk can do huge things. Hulk really means huge, doesn't it? Anyway, the force is huge. And what would happen if the Hulk jumped? That force would be so high it would just break the concrete. And that's true. That's fun. Okay, it's not real. It doesn't have to be real, but it's fun to play around with situations like that. Superheroes, big superhero fan, science fiction fan. So I like to do stuff like that too. So, but if you want to look at that, it's the same physics that we had over here. It's the same thing. Okay.